Hey, 12th graders. So we are finishing up 14.3 today. What we've talked about so far in this lesson is that we've talked we've really leaned into the area underneath the curve. We've talked about why we care about the area underneath the curve. And then we talked about it in kind of like these small steps in the beginning that, like, you can find the definite integral of an equation, and it gives you the exact same area as if you had like created a geometry problem of the area of that shape. And then that was the very beginning. And then we started to explore more of like, okay, what if we add on a couple more steps? And so our last example that we did was like, okay, what about just between this equation and the x axis? And what that means is that we need to figure out what our bounds would be. So sometimes we have that missing puzzle piece of like, well, we normally have bounds, and how would we get that now with just this information? How do we connect now those dots when it isn't just given to us at the beginning? And that's pretty much what the rest of these notes are here, is that we're trying to, it's still this idea of area underneath the curve. We now have the tool to find the area underneath the curve. But how do we piece together what we have and what we want and connect those dots? And so try and really focus on, what am I upset about? Why can't I move forward? Can I not move forward because I don't have bounds? Can I not move forward because I don't have that equation? So trying to figure out how to take the thing that you don't know how to manage and turn it on its head, so you can be like, well, if I don't know that, I need to figure it out. And how do you do that? So, example number three, both of these guys deal with what we call composite figures. And composite figures are when we have multiple shapes that are brought together to create one bigger uh, uh, shape, like a composition musically, right? Composition musically is taking a bunch of pieces of a song and putting it together to create one big song. Is your layman's example of a composition, but it's that idea. So we're going to find the area enclosed by this curve and now another curve and the x-axis. So you'll notice that once we start to add in more than one curve, that's when we need to start taking into consideration composite figures. So your first step with these guys, do I understand it visually? So you need to graph it. Put it into your calculator, look at it, and then determine visually what area am I talking about here. So we go to graph this guy, x plus 3, enter. And then we're going to graph the other guy, -2 times x minus 2 cubed. And then now that we have it on our graphing calculator, that's great. I am really a big fan of also just quickly sketching it on your page, because I think it helps. I think it makes a big difference in regards to your understanding of the situation. If you can just have a diagram that you've drawn and be able to write down new information that you have. So we've got a square root graph that looks like this, and then that's not exactly what I was going for there. A cubic graph that looks something like that. And so if we're trying to find the area bounded by these two graphs and the x-axis, we're talking about where that shading would agree. So below the curve would be below the blue. That's kind of easy to see. Below red would be like all of this, right? All of this is below the red. And so where they would agree, where that shading agrees, is in, especially above the x-axis, is in this little part right here of the shading. So all of this. This is the area we are trying to find. So since we have two equations, we have two shapes that are really being put into play here. And so we need to be able to divide up this one big shape into two smaller shapes. And how we think about that as mathematicians, trying to be able to break this down into parts that I can manage, is that I can manage finding the area underneath one curve at a time. And so we need to figure out where is the area colliding between one graph and the next. So I want you to kind of think about between these two graphs of these two equations, where does the area start to collide? Where do those areas collide? And I want you to kind of take a guess, make a hypothesis of where would the two areas interfere with each other. So hopefully we can kind of see here that like if we were to put on blinders like a horse and try and not spook, that like we can find that area, that area, that area, right? Everything up to this point right here, it's only underneath one curve. It's when we start to then think about them both at the same time with this other curve over here that we start to freak out, right? This looks totally manageable. This looks less manageable. Versus the other way around, that like all of this seems, it's a very small amount, but all of this also seems like fairly manageable, right? It's just the area underneath that one curve. And so it's not until we start to think about them both at the same time that we start to kind of feel a little iffy about this. So what if we went in here and just drew a line and broke up these two areas representing the two different curves where it starts at that point of intersection? This point of intersection is where your areas collide. So that's the answer to that thing that I just asked you. Your point of intersection between the two graphs is where your areas kind of come to meet. Once you pass this boundary right here, you move from the area underneath one curve to now the area underneath another curve. So the deal with composite figures is that we want to be able to find the area of one and find the area of the other and put them together. We've done that quite a bit now. So we know that the area total here will be equal to the area of, I don't know, I'll call it A, plus the area of B. And we'll call this area A, and we'll call this area B. So if we wanted to break it up one by one, well, okay, the area underneath, area A, underneath this first curve, which you can see is blue. And if you scroll up, you'll see that blue was your square root function. So just dealing with the area under A, we're finding the integral of this guy, the square root of x plus 3 dx. But our question is, with what bounds, right? From where to where? To find the area, we need to know where we start and where we end. And so kind of circling back to our previous example where we weren't given bounds. And that's something that we need to focus on. Of like, okay, can I go find those bounds with my calculator? Can I go find where it starts and where it ends? So with this guy, where the area A starts to the farthest left is this point right here. Remember that we only care about the x values from this x value to the other x value, because notice that as we kind of like scan from here to here, we're always following along this x-axis scale, right? So as we're scanning from left to right, okay, we start at this point and we end at this point of intersection. So those are going to be our bounds. We just don't know what they are yet, but we can totally find them. I want you to go ahead and find your x-intercept, this point right here, the x value of your x-intercept, and I want you to find the x value of your, the x value of your intercept, and then the x value of your intersection. And then that will tell you the bounds for this guy. So I want you to find the x value here and the x value here. In order to find that x value for our x-intercept, we would go to our 0 in our calculator. It says, hey, which graph? You say this one, and then lower to upper. And our x-intercept is -3. So we're from -3, and then this x value here would be the intersection between the two graphs. And the x value of our intersection is 1. So from -3 to 1 is going to be the area underneath that first curve. So we're going to take this integral and start to put bounds on it. From, -3 to 1 of the square root of x plus 3 dx. We don't know how to find the integral of a square root function. It's the chain rule. Again, we are seeing this a lot now, that a lot of the things that we don't know how to find is a chain rule situation. You can find it if you ever want to go look it up, but we just haven't learned it. And so what we're going to do instead is use our calculator. So remember that your calculator can calculate that integral value for you. You go to menu, you go to calculus, and then numerical integral. And then it pops up like this. So we put in our bounds, -3 to 1 of the square root of x plus 3 d what? dx. And that answer is 5.33. So that is the area of A. Now, in order to find the area of B, it's the integral of our second equation, which is a cubic right here. So the integral of -2 times x minus 2 cubed dx. And again, with what bounds? So we know that we're starting at 1 and then scaling across. Starting at 1, we end where it crosses the x-axis, this point right here, which would be our x-intercept. Going in back to our graph, going in and finding that x-intercept, we just click on the correct graph, give ourselves enough space to make sure we find the right one, and our answer is 2. So we go from 1 to 2. Well, this is a cubic, which we can expand because it's a polynomial. We can expand to make it look like how we like to have it for our power rule process. So we can find the integral like by hand of this guy. We're not going to do that. We're just going to go ahead and practice using the button in our calculator. Oh, so sorry. The button in our calculator to find that integral value, that definite integral value. So I would like for you to find that value on your own. Go and find out what that area is underneath. You plug it all in and you find out that it was just equal to 0.5. Adding those two guys together, because that's our final goal. So it's actually, I know it feels really weird to write this at the top, but it's a really good reminder to be like, oh, that's right. I need to add these two areas before I'm done. So the total area is then equal to 0.5 plus 5.33, which is equal to 5.83. And that is your answer for example 3. So still not changing anything. We're still practicing the same tools. We're now just kind of adding one more step in of we need to make sure that we can divide up spaces to be able to deal with wonky looking shapes to make sure that we can accommodate any shape that gets thrown our way at any point.